will be given by Richard, our PhD student here. And it's going to be basically about the work that he has been doing since he got here. It's a compression optimized for worst-case optimal joins. Richard, the stage is yours.
Thank you. So yeah, I'll talk about my ongoing work. So obviously this is still a work in progress. Not everything is finished yet, not everything has been done, but I'll just show what I've been doing so far. So first some context. As we all know, joins are kind of a big deal in databases and database research, and we've studied them extensively, but some say that they are not optimal in some cases. So the classic example is if you would have like these three relations, R with A and B, and S with B and C, and T and A with C. If you do the natural join on them, so R on S and T, so on A and A, B and B, C on C. This is also called the triangle query because you have these A's here, B's here, C's, and you connect them. So I think fairly recently it's shown that like the output of this query will be in big O n to the power of 1.5. But there's inputs for which basically any intermediate result for any binary join plan will always be in n squared. So that means that you're basically doing unnecessary work, and the TV is gone, which is not a surprise. So it's back. Okay, so yeah, basically there's inputs for no matter how brilliant your joint plan is, you'll always do more work than you necessarily have to. As an example, this would be data for which this happens. So if we first join R on S, we get this sizable table, yet if we join T on this, then we get a much smaller result. And this is true for any join order. So if we do this with T first, then yeah, same thing, or S on T, same thing. So yeah, basically we want to do something about this. Unfortunately, we have people that are better at maths than we are. They write papers at pods, and they came up with a class of join algorithms called the worst-case optimal join. And so basically the idea of these joins is that they guarantee to not do, that their running time is bounded by the output, by any bound that you have on the output size. So in this case, that would mean that your runtime would be n to the power of 1.5 rather than n squared. Now they do this is by not joining, just not doing this binary join where you first pick two relations, join them, and then get the next one, but you actually look at it as a variable at a time rather than relation at a time. And one of these worst case optimal joins is called the leapfrog try join. And what I'll do is I'm not going to go into like the mathematical stuff behind the worst case optimal joins and the complexity guarantees, because to be honest I don't even understand all of it either, but I'll just walk through like an example computation of leapfrog try join, and hopefully that'll give some sense of what a worst case optimal join looks like and why it works. So so we'll do that for leapfrog try join. Leapfrog try join is based on leapfrog join, so without the tries, and again this is got a lot back with the USB-Cs. It's
I think it's the HDMI.
Okay, so it's based on leapfrog join. Leapfrog join only works in unary relations, so if you have only one key basically to join on. So as an example, say that we have these three relations A, B, and C, all with one variable, and we want to join these, or find the intersection, however you want to call it. Then how this leapfrog join works, it first sorts these iterators by their first position. So you have A first because that has 0 at the start, and then B also 0, and then C has a 2, so that's like the last iterator. You record the first value of the last iterator, so that's 2. And then the first iterator tries to get in position with the last one. So it tries to find 2, can't find it, so we'll end at the first position afterwards, which is 3. And now B tries to get in position with A. Can't find it, so it ends up at 6, and C does the same, ends up at 8. And so we continue until we basically have a match, because in this case they're all in position, so they're all find an 8. And then C just continues to the next variable, and the whole thing starts again. Obviously, like this, so this is a fast way to find an intersection, but this in itself is not new, and this is really annoying me. Is it? Okay.
I think it's the cable that...
Yeah, I'm not even touching it though. So see, like, okay, well. So this in itself is not new, but this is the basis of leapfrog try join. And what's important about this is like all these seek operations. So these seek is basically just a binary search or a galloping search actually. And so it's important that these seeks are in log n, otherwise you can't guarantee the complexity guarantees of leapfrog try join.
So the A, B, C have to be ordered here.
Yeah, that's we'll get to that later, but it's basically the mild assumption of worst case optimal joins is that all your relations are always sorted in whatever join order you have. So yeah,
that adds another.
Yeah, I mean actually like the sorting is probably heavier than the whole join itself.
Yes.
We're just gonna ignore that for now.
Oh,
but yeah, it is obviously a problem.
If that means you get from n squared to n log n, you're still better off, right?
Well, yeah,
In
asymptotically, theoretically, yeah. Whether that is in practice, that's of course will depend. But yeah. So now we want to do this with multiple relations. So like say that we have this relation R. Basically, what you do with leapfrog tries when you present your relation as a trie, hence the name. So how do we do that? Well, if we rotate this this relation like this, basically if you gather all these zeros into one value, this is like a trie presentation of this. So like you have the root node is the relation symbol, and then the first level has these nodes which relate to like the distinct values of A, and then the children of this A is, for instance, all the B's that could occur given that A, and this is all the B's that could occur given that A. So there's only the zero here. And we're going to use this, well, this is almost like an index in itself. We're going to use this to perform the join. Again, I'll just walk through an example computation. I hope that will make it a bit clearer. So in the leapfrog try, you join a variable at a time, and this in an order that has been set somehow by an optimizer. In this case, we start at A, we go to B, and then to C. So first we're looking at our A's. So we have the 0, 1, 2 in T and the 0, 1, 2 in R. We look at our first variable, we see that both have a match, just because they're both 0. And then we go to the next variable, which is B. Now we only consider the B's given that A is 0. So in R, we don't even have to look at these ones, we only look at these ones. And that's of course where the trie comes in, because you can easily see which B's are relevant. In S, there is no A, so nothing is bound yet, so you can look at all of them. Again, we have a match. And now we do the same things for C, and we only have to consider the first half of the C's in both S and T. And also we have a join result, because 0 match in C, they match in B, they match in A, so we have our first join result. We look at our next C, again we have a join result, another join result, and now we've exhausted our C's, so we go back to B, look at the next one, and we basically continue this thing. So another join, and another one, and now finally, so of course, there's only 1 0 here, so we don't even have to consider those ones because we've got a match in the first place. Going back to B and finally going back to the A, and we do the whole thing again. Anyway, the point of this is, of course, that what is try join does and what worst case optimal join in general do is, given some kind of A, they'll already start looking for the B's, and they'll already start looking for the C's that could apply given that A and B. Rather than first, collecting everything that joins on A and then doing everything on B, and then, that way you kind of prevent doing unnecessary work.
But how does this compare performance-wise to an ordinary hash-based approach? Space-wise, this is worse. This is terrible.
In what sense?
The trie administration becomes too complex.
Yeah, but a trie is not an actual. I'll get to the back in the next slide. You don't have an actual trie. So how you would implement this is basically you actually just have this. You have a normal table, and for instance, if you are here and in A, what it really means, of course, is that you're at this position in the actual table. And for instance, if you want to go to the next A, you could implement that with like a seek operation. So you basically look for the first A that doesn't beyond 0. That's just a normal.
But then it still stands actually. How does it compare performance-wise to a normal hash-based approach?
Well, asymptotically speaking, it's better. So this would be an ON to the power of 1.5 instead of n squared. How it is, I did a couple of tests actually, and it was fast. I don't have exact numbers, so I can't help you in that sense, but it was faster for this triangle query. I would honestly assume that for a regular binary join, this would not help you at all because you have overhead that's probably
I would
not
question it. I think that if we would have a perfect hash, then the hash probably would be actually extremely fast.
I compared it to this query. I did this triangle query in Hyper, and I did it in like the basic simple system of Delph, and which is the relational AI that uses worst case optimal joins, and that seemed for that query seemed to perform faster because it's exactly made for these kind of queries, right? Where you want to get rid of these intermediate results.
We'll continue.
Yeah, okay, but one thing to if I'm not wrong, but I'm not too familiar with the stuff here, but you're talking about the two-way hash join, right? And doing 3 of them, as opposed
Okay.
to.
Oh, sorry. Yeah.
You can actually do an n-way join, this one, and you can, how you implement this idea of the try, whether you implement the lookups using the hash, or the lookups or the seeks. Now you need to order it, otherwise you can't do it.
Well, you don't I mean, for leapfrog try join, yeah, you kind of do it with an index, but in general, you don't have to worst case optimal join with sorting, right? You could do that with hashing as well. The real requirement is that you somehow index your relations according to the variable order that you're going through these variables. In this case, the indexing is done by sorting. Yeah.
You could probably think of this even doing a multi-way join with a hash, but I have to think of it more. Or they thought more about it.
That's the hope.
It is different whether you do it as a two-way joint or one multi-way joint.
Yeah, so I thought you were referring to like the more like a binary join, but that's different.
No, you actually can combine it all in one.
Yeah, no, that's true.
Then it's actually theoretically maybe it's linear in the size of the 3 relations. Modulo the collisions you have to take care of. And performance-wise, since it's all actually masking, it's you don't even need the masking. It's actually linear, potentially linear in size of the relations modulo the exceptions.
It would be linear.
Well, if you play with hashes, unless they are perfect, you may have collisions. So in the end, actually, you may have to check actually for the values for the collision chain.
Yeah, but for each A, you have to check for each B, and then you have to check for each C. So it's
It's not linear because it's hard to do. Because you have no, if you just go ahead, you have no, it's hard to do the multi-way join correct.
Sure.
Because you cannot simply just iterate over one of them.
Well, anyway, you continue with the try. Yeah.
All right.
There is a question on the table which will come back at some point. How does it compare to an optimized hash-based solution?
Yeah, that's an interesting question itself. I would know by now, but anyway. So, like I said, this is my favorite sentence of a paper on the worst case optimal joins. So yeah, you have to pre-index all the relations in every possible order for any kind of join that you would have. But that's just a mild assumption, so we're actually not going to care about that. That's not even the problem for me. So yeah, we know that data must be indexed. In this case, it's always even sorted in advance. And in fact, that would even give us kind of advantage if we want to compress data. Just to illustrate that point, if we were going to apply delta compression on this uniform random data set, that's not really helping us out at all. Yet if we compress it, then obviously we get much smaller encoded values and we can actually compress this. Same goes for running encoding. When we start sorting this, we actually get a couple of runs, and so you get a nicely compressed data set. So all of that is good, but the problem is that running encoding and delta compression are not exactly known for their RandomX efficiency. So for instance, if we have this delta encoded values, if you want to get the middle value, which you would do if you do a binary search, you start at the middle of course, then you actually have to know all the values that came before it, which means that binary search is now in ON, which means that we can't guarantee our complexity, or we can do our complexity guarantees in worst case optimal joins, hence we cannot do worst case optimal joins directly on this compressed data. So yeah, that's kind of a shame because we've sorted this data anyway, so it would be nice if we could also compress it nicely. So basically, the problem that we have, what we want to do is like find new compression schemes that have compression ratios that are comparable to delta and RLE in the cases that delta and RLE would be applicable. Yet get a random access that is much closer to like an uncompressed case. Particularly, like we want to be able to have an efficient seek function because that's what these worst-case optimal joins are based on. More generally, we're just looking for a compression scheme that supports worst-case optimal joins, and it would be nice, of course, if we could even make it faster. Those are basically two compression schemes that we came up with. The first is PAX multiple frames of reference, and this tries to, be good at cases that delta compression is good at as well. It's based on frame of reference, hence the name. But instead we use multiple frames of reference. I'll just walk through it in a bit. We use patching. We use bind-align packing. So like we don't actually, if maybe you could express like the largest value in your list with only 3 bits. We don't do that. We would do it in a byte then because it's just a bit better for random access because you can just use native data types. And we compress in blocks. I'll get back in that in a bit. So, just a quick recap. It's based on for compression. So, if we would for compress this nicely sorted list, what we would end up with is this list. So you have, the lowest value is the reference, and you subtract that value from every other value. And hopefully you could store this with less bits than what's on top. In this case, we actually can't because we're doing it in bytes. So this would still require 16 bits, just as this one, because it won't fit in a single byte. RandomX is obviously, it's very easy. You just get your delta at position I and you add the reference to it. When we said we use multiple frames of reference, so for a given number of elements we use one reference, and then the next number of elements you could use another reference, and this way you get a bit closer to what delta does. Especially if you sort the data, then you just end up with smaller deltas, of course, at the cost of storing another reference, but this could help you out. The number of references is, I'll get back to this in a bit actually. I should get to this now. So basically you have this parameter R, and R tells you how many elements are associated with the same reference. So 2 to the power of R, in this case R is 3, so 8 elements are associated with one reference. And because we do this, you can just find a reference associated with some position by a simple bit shift rather than doing division, so that makes it a bit faster as well. And R is configurable, which is, if you have very small steps in your data, then you wouldn't really need a lot of references. Yet if you have something like this, then it would be preferable to have a bit more references because you could, squash the encoded values down and still pack them in.
For your information, you may have a look at the Mosaic branch of MongoDB because it has that all included.
All this? Okay.
Even worse, frame of reference with delta encoding, with redundant encoding, all mixed.
But then delta encoding wouldn't really help you out.
No, that's not right.
Okay.
So mixing actually multiple frame of references actually is there. It's like even dynamically decided how long the thing should be, and it's also actually at the bit level compression. And
well, bit level is something that I'm not really sure if that would be. But I agree.
That's a different issue.
Yeah.
So multiple frame of reference, and actually even using multiple actually compression schemes within the same column actually pays off. I've seen in many situations that 2 or 3 compression schemes could give you a better compression than you would normally expect.
Yeah, it makes sense. For instance, if you do delta compression, then you could probably do running for coding afterwards.
For information, does Mosaic for these compression schemes support random lookups?
Yep.
No.
Let's put it differently. So the compression is complemented with actually the relational algebra operators correction, selection, and join, which actually take care of actually how you should recover the underlying value. Okay. So yes, if you have the delta, then you have to
just for the reference, the very idea of this work is, given an arbitrary index in my compressed space, I want to instantly know what the actual number is there.
Yeah.
Right?
Yeah, well,
I don't want to do anything. I just randomly look at any position in the column, and in the compressed column, And they can derive the original byte.
For those compression schemes which actually allow you to do that, it's done. It's actually how it's being encoded.
The point here is actually to derive a compression tree that allows you to do that. Here the point is to invent a compression scheme that allows you to do that.
Yeah, well, that's fine. So it was the recap of the frame of reference. It was the recap of the frame of reference, and so it's the recap of actually what's available in these corridors.
Apparently, yeah.
Okay.
So if we do this, we still have one problem because we have this one value that still won't fit in a single byte. We call this an outlier in our encoded values, and we need to do something about this using patching, which I also realize it's not new in itself. But so basically, the idea here. This value that we couldn't compress at first, we call an exception. We store it in a different table, and then instead you just what you store here is an address into that exception table. Of course, somehow you need to know whether this value is an exception or whether it's a normal value. Again, to make random access possible, we store that in that single element. So the first bit. We sacrifice the first bit and it's set to 1 if the value is an exception. If so, then the remaining bits are an address into our exception table. If it's not set, then it's just a regular delta. And so basically random access would ultimately end up something like this. So you do have an additional branch now, unfortunately, because of the patching. But otherwise you could still quite fast you would get your value.
Challenge is to predicate that.
Yes.
The challenge is to predicate that.
Yeah,
that should be
To make
easy.
it branch free. It's not easy, but it might be possible.
Well, yeah, it is easy because actually the bit becomes 0, 1 with a multiplication.
But is it worth it actually?
Well, that's a different issue.
If you maybe have 1 or 2 exceptions.
Yeah, so the branch prediction of this would be very easy, of course, because you don't really have more than maybe a % exceptions.
It should be easy predictable.
Yeah, so I'm not sure if predication would really help. And so finally, the compression happens in fixed size blocks. So the idea being here, if maybe you have some data set that some part has very small steps and other parts are large steps. So it would be nice if you could have a different R for this part and a different R for that part. So that's why, it's the compression happens in blocks and not for the entire array at a time. So that's the main idea of that one. This is just bolting everything together. So there's some header that says how many values are in the whole compressed thing. Per block we keep the maximum value in there, so you can do a bit more efficient searching, and then just point it to all these blocks. And every block is just inside that is what I just talked about. Of course, we did some experiments. So to evaluate the compression ratio of PM4. I tried a couple of data sets. So first just basic generated data sets are not so interesting. More interesting is the Stanford Large Network Dataset Collection. It's a collection of graphs basically. So for instance, they crawled Facebook's, Jesus, is this ever gonna stop? They didn't crawl Jesus though, they crawled Facebook, Google Plus and Twitter. It's basically like these friends tables. Then Tableau, so was helped by Bogdan. I basically got a random tables, extracted integers out of there and sorted them and pretended that is real data. It's not exactly, of course, but it should be a bit more real than just generating something. And then TPCH, because we're database scientists. And then compare that with some reference implementations, so delta compression and B delta compression. Basically, it's all delta compression, but the one uses patching, the other doesn't, just for fun. And then simple and blocked implementation. So simple would mean that we don't use the blocking, basically. So the whole array is compressed at once, whereas blocked implementations, you partition it in fixed size blocks that I talked about before. And all of that is compared. So overall, these are the results with a couple of different compression schemes. So like these ones don't use any patching, and you can see that, because of that, it's not really doing such a great job. So like on the average, it's just a compression ratio of 2, which you would often get simply by doing prefix compression. This is delta compression, definitely doing the best, but PM4 is, at least on the average case, quite close to it. On the extreme cases, delta is definitely better. And this is like without the blocking. This does use blocks, and you can see that there are cases where blocks seem to have a bit of a positive impact on the compression ratio. Of course, it does depend on the data set. So, TPCH is very regular, so, there's not really going to be any exceptions. So, it doesn't really pay off to have a patching mechanism. But if you look at the Tableau data, which is quite different, then you really do see the point of doing that. And Snap is somewhere more in between. Also tested what is a good size for these blocks. And you can see that if the block size is too low, you basically have too much overhead in storing a pointer and all that. So you get these really low results, whereas if it's too large, then basically you get back to doing everything in a single array. So here, it seems that something around 8 to 16K is fine, but it's still, I wouldn't really call it science. I'm not sure if it's that's always true, but for now, I'm going for that.
Question, since you observed in the previous sheets that actually it's strongly dependent on the data distribution.
Yeah.
So why stick then to actually a fixed block size? Because it seems that a variable block size in combination with the data distribution gives you much better.
Yeah, in general that would be better. So I should be elaborating on that probably. I would say in general you should probably vary that. Just the system that I'm building it in is JIT compiled. So if you would have a different parameter for every table, that also means that every function is going to have to be compiled again as well for every compression. You just get code exposure, which is something I'm a bit wary of. And that's in that case. But in general, I would say you probably want to vary it as well.
In the end, you will just look at the MBL and MDL complexity factor. And then this means actually you look at the code size and the size of the compressed data. And that total should be more or less optimal.
Yeah, fair enough.
And this means that since the data size we're playing with is already pretty large, I would not be too afraid and too quickly with code expansion.
Fair enough. Yeah, no, you're right. It was at least worth.
The algorithms we're playing with are pretty small. Perhaps they end up in a few kilobytes of code. Now throw in 1,000 different variants. Who cares?
Yeah, well, at least with the weld thing, obviously during my thesis, I did see that problem. Let's hope that Julia is a bit better in that regard. It's still Stanford though. But yeah,
that's no proof of politics. in terms of software.
No, it's quite the opposite actually.
Okay, well then you're more blunt than I am.
It's terrifying what they get away.
That was my point. Yeah. Anyway, so there's that. So there's also we also wanted to mimic running encoding. So basically, the first thing you want to do if you want to do any kind of random access on running encoding is to not use running encoding, but run precision encoding, which is almost the same. But rather than storing like how often a value occurs in a row, you store where the run starts. Of course, you need a bit more. It's a bit less efficient because storing a 7 needs more bits than 3. But a good part about this is you could just do a binary search on a position table and you would have your value. Of course, binary search is not really that great either, so we'd like to do a bit better. So the first idea here, and that's not new, is basically this entry table where if I'm looking for a position I, I'll look for a petition that covers that I. So for instance, for 13, I would look into here, and then this tells me where to start my search. And from there, I can just do a linear search and quickly find the run that covers that position. So to give you an example, if we're looking for 12, that's in this partition. It tells me to look at run number 4, so the 5th run. Obviously 7, that's not 12, so we're looking to the next one, and we have our value. And so we don't have to look through most of the data set this way. What I think is new though, but please tell me if it's not, is this. So rather than storing all these positions in a normal table, you can just store it in a bitmap. And you can use this bitmap to, oh Jesus, I really have to clean the screen for this. Okay. So yeah, so this just converts to that. And you can use this bitmap to quickly find the position as well, the run associated to some position. So basically what you do is you look at the 13th bit. If you're looking for position 13, you discard all the bits that came afterwards. And then you basically count the number of, maybe if I just keep sending like this. So basically every one here represents a run, right? So if you count the number of bits that is set to 1, you know at which run this value started. And Intel has this pop count thing for this. I think it's Intel anyway, which is pretty fast, and so you can get this in pretty quickly. And then you know that you just have to look at the 6th run, and that's our value. Obviously, this only works if you have like no more than 64 bits in your run length encoded value, because that's just the integers that we have. But of course, you can do this for each block of 64 values. So you have this position bitmap for each block, and then also you store the number of runs that preceded that block. And so then for any given I, you would just find the bitmap associated with the block, do the bit count as I just did before, and then you add that to the number of runs that precede that block, which we already calculated anyway. And there's our index. So I did some experiments with this as well. So I tried out a couple of these run position variants in C++. So we have the entry table with a linear search, with a scalar linear search, with a single linear search. And also this position bitmap lookup. Did a large number of times on a small array, because I don't really care about cache misses at this point, but of course we'll test that as well, for differing run lengths, because if you have a lot of run lengths, if the run lengths are on average small, then there's a lot of positions to look for. If you have very large runs, then there's less positions to look for, so that will also make a difference. And record the size per lookup. So blue is just a simple scalar linear search, and indeed if the run length is small, so you have more positions to look for, it takes a long time. But after some point it's actually faster than SIMD, which is green and orange. But using the bitmap version is actually faster than anything else in pretty much every case. I think it should also even be more efficient in terms of cache, because you're only storing this bitmap now rather than having this entry table as well. So yeah, that's pretty nice, because now in 5.5 cycles you can find your value basically. So yeah, that's a bit what I've been doing so far. So yeah, implemented a couple of RandomX's optimized compression schemes, one that apparently already exists. And then this run position encoding that with efficient RandomX's as well. And yeah, there's still a couple of things to do. So for instance, I mean, I've been working on this RandomX's, but the whole point, of course, was doing worst case optimal joints on this. I'm starting to work on this now. The thing is that where I'm building it in, like this leapfrog trijoin kind of assumes this whole row store model, which isn't a problem in itself, because of course you could quite easily convert, make a column store that look as if it's rows, but the problem is a bit with writing an iterate function. So just to show, like this is an iterate function in Julia. So say the axis is your table that you're iterating over, and you have some state that tells you like I'm at this position right now. Of course you would first check, am I still looking at a valid position, and if that's true, then you will return that value and you increase your pointer by 1. Now if you have these 3 columns, then the naive way of doing this is by calling just basically this iteration 3 times, but the problem with that is that you would have this check being done 3 times, and we don't want that, of course, because that's just unnecessary, because every column is just as long. So instead you should do something like this, where you do 1 check and then you just get the value as so. But the problem is that this iterator for the run length encoded values looks a bit differently. So this is what that looks like for a run length encoded column. Basically the problem is that with a normal iterator for an uncompressed vector, you check at the beginning, like, am I at the end of my total array? And if not, I can just return a value. But here you have to check, am I at the end of my run? And that is actually different for each column. So for each column, you would have to have a separate check, and that makes just a very simple iteration actually quite costly. So yeah, I have to do something about that. So yeah, the problem is that we just cannot really share this state anymore. The question, of course, is like, yeah, why even try to retrofit this row store thing on worst case optimal join and maybe do it directly on the columns? I'm looking into that right now. I'll have a talk with Todd Veldhuizer probably, which made the leapfrog trijoin, and see if we can do something about that. And otherwise, yeah, I didn't look into like how fast compression speed is at all. So that could definitely be optimized. Like also finding this R in a minimum time. That's something that still needs to be done. And that's it.
Does anyone have a question?
Yeah, I do, just curiosity. The last plot that you showed, what were the axes?
This one?
I think so, yeah, average.
Yeah, so sorry, this is the average run length in the array that was being compressed basically. So that means like the run length for free would be that you just have a data set like this. Like 1, 1, 2, 2, 2, 3. Okay. So this would be a run length for free on average basically, or actually exactly. The longer the run length is, the less positions you need to store in your compressed data set. So the less positions you need to look for as well. So this is why the blue one takes a longer time for lower run lengths because it's more positions to look for.
So in this case, actually, the underlying data is still uniformly distributed?
Yeah.
Skip that. Go immediately to Zipfin. Try to see what the effect is on Zipfin distributions.
Alright, yeah.
That's absolutely much more interesting to understand. And probably you can get more gain there. Especially if it's sorted.
Yeah.
Then actually you will end up actually with blocks which are much larger than what you probably anticipate.
Fair enough, I'll try that.
Yeah?
Yeah.
But then you also need to consider likewise but differently Zipfin distributed lookups. If you have Zipfin distributed but you have uniform lookups, given that if your original data is Zipfin distributed, you still have but you see about the average number of runs, and you still have the average number of runs. Because whether your average number of runs stays like this, or whether you have like in these 9 values 3 runs by having 6 1s, 2 2s, and 1 3, shouldn't make a difference. On average, you have the same number of lookups.
Fine, but the point is actually go away from the uniform distribution. Yeah? Because you probably find more leverage there. That's the hint.
Alright. You had a question?
Yeah, I have another question about your iterators at the end.
Mm-hmm.
Interesting problem actually. However, if you have separate columns of the same table and they have different, and you have them run length and code, of course, given they have different distributions, they have different number of runs.
Yeah.
What does it actually mean with this kind of iterator if you iterate in the compressed space, if you want to kind of synchronously iterate? You know, if you say next on the 1 column, you go to the next run, or you go to the next value.
This iterator, it will act as if it's an uncompressed value, so it goes to the next value. So,
Okay.
so you keep track of how many values are still left in a run,
Yeah.
and you just keep subtracting the number. You basically only return the last value that you returned.
Good. But then I think you can still do this because you have this run length encoding, this positional encoding, where you can, given a position, quickly give the value. So you could actually virtually iterate over your position still, even in your iterator, and still count and check.
Yeah, but I mean, it's kind of fast, like doing this in 4 cycles, but it's not as fast as doing simple iterate. So.
Okay, but then for each iterator you have to. Okay.
Yeah, it's actually it is more efficient to just otherwise because you're just doing a check like do I still have a value left in my run, and then you just return the same thing. That's faster than doing this whole.
Okay, but then you have to know for each for each run how long it is. So you're inside the run, you need to keep state of every run to know when you're iterating over the non-compressed, virtually iterating over the non-compressed, when to switch to the next run. Right?
Something that I think I actually want to do is. So say that you have like this sort of data with 3 columns. So basically here you can see that this is the longest run. This is a bit smaller runs. But you always know that if this run ends, as long as this run hasn't ended, you probably don't have to check this one. So you can probably leave out this check. It's just not always the case. But maybe like in the compression scheme, you could kind of force it that a new run here always starts when you can somehow lock them together.
You can have artifacts where they're like happen to be boundaries happen to be synchronous.
Yeah.
You know, the first value in the second, the lowest value in the second column and the first column is 2. Is 3. So actually your second column would change. No, well, it's also 2. So after the 1, 2 comes the 2, 2. So there is no 2, 1 in your data. After the 1, 2 comes the 2, 2, and then you have to check the first instead of checking the second. Yes.
That's, I think ultimately you should just, for the worst case optimal join, you don't actually care about getting the whole tuple. You're always looking at just at a variable at a time. So it doesn't even make sense to do this whole thing actually, I think. I mean, still you want to have proper iterator performance, but it's, yeah.
Okay, from a theoretical point of view, did they extend it actually to the clique joins? Because the triangle is of course easy. The next step of course is go to 4. And then of course you can have a circular one join, but that's not interesting. Then of course you will be interested in the clique, where actually every other component is being done. So is there any theoretical bounds on if you're going from the triangle to the clique?
I'm not sure. I'm not sure if there's a time bounds for this.
Because if you go to, let's say, 4 points and then you have a clique, then you can address it as one problem, but you can also understand it's actually a combination of 2 triangles in the right way of doing it. Okay.
Trying to stay ahead of that, sorry.
So, okay, but
I'll have to admit I'm not sure. I think I read something about clicks in these papers, but yeah. I think the point is if you have some kind of bounds on this, then it should be able to write a join algorithm that will do this in optimal time.
okay, but the underlying question behind it is because if triangles in many computer science environments is a very natural next step. Triangulation in image processing is basic.
Yeah.
In databases, we stop with the binary with joins with 2 arguments. So the next challenge would be adding the triangular join algorithm to MongoDB, cut all of this, or not?
I think it should, but I'm honestly not.
Okay, well,
yeah.
I'm not asking here. This is not a PhD defense.
Yeah, of course.
It's just putting some questions on the table.
Yeah.
When sometimes can think about it. That triangle is one step in a click environment, so you should at least know what's happening there.
Yeah.
And for MongoDB kind of environments, perhaps adding a triangle join might be itself an interesting little addition, which can cope with some of this stuff. Yeah.
While I am not in detail familiar with the original work of worst-case optimal joins, to the extent that I understand what Richard just presented, there are 2 things. One is it's worst-case optimal, meaning we can give some theoretical bounds.
Yeah.
And there might or might not be, we have to check that, a prerequisite for this bound that we actually have a triangle join pattern. The algorithm itself, as far as I can tell, from what I've seen, is just a multi-way join.
Yes.
There is not even the 3, or how they are related is not there. It's just we have a multi-way join. And that's the whole idea. The whole idea is to avoid intermediate results materializing or creating or calculating that are bigger than the final result by not considering one join at a time and finding a smart join order, which, as we have pointed out in the beginning, can easily be defeated by data constellation where any sum, or in the very example he gave, in any 2-way intermediate result is larger than the final result. And by doing a multi-way join, this is avoided. And leapfrog tree join is one way of, given some assumptions like this negligible, as they say, assumption of every data is sorted, gives us a way to efficiently, at least on paper, and here's a way to get it also in practice, calculate that. That should be unrelated to shape our join process. theoretical bounds might be only possible with I cannot tell that, but the general joint should be unrelated. Correct me if I'm
No, I think you're right.
wrong.
Yeah.
Should be unrelated to the fact whether we have what kind of joint graph we have.
Yes, I agree. So why not actually implement that variation in the joint path in the body?
Why not?
The joint path optimized currently actually is the poor way of doing it. If you're doing it optimized way,
The paper is there. It's the question of implementing
Yeah.
default dry joints in whatever system. Whether it's weld or monadity doesn't really, or ductily, it doesn't really matter.
Yeah, I don't think so.
I
I don't see this
Tomorrow.
that thing happening. Sorry.
I can probably add some things to it. There's a master thesis discussing it in the more general case of higher clicks, but I don't remember the conclusion. And there is also a paper where they tried it in practice on at least the 4-click, and they show that it definitely works well for the 4-click as well as for some really selective joints of a path, of a linear path, or of the combination even of a path and a click.
Any more questions?
I have just a quick question. Has there been any kind of research into the popularity of these kinds of joint patterns?
Good question.
Because I mean, I don't know. I've never seen anything.
I
like it, but-
haven't looked for it. I haven't seen anyone referring to this.
Okay, because
well, there's a simple
So, yeah,
sanity
it's a
check
good
that you
question,
found them in your benchmark. In the OpenBI or the benchmark, which is, let's say,
Sorry, this benchmark.
Yeah, but
I didn't very too much, but there are very few joints in
They
the
are?
queries. Very few joints.
yes, yeah, oh yeah, of course, it's all. Yeah, you make a first flat table in Tableau. Yeah, that's true.
Yeah.
Yeah, and then a little dimension lookup.
I would expect this in graph queries.
There's high
Graph
In
queries,
joint
yes.
patterns,
Yeah.
not really in the normal relation.
Yeah.
There's a lot of research about triangle queries in graphs,
Oh yeah.
then always connected to that. And well, there it's used in all kind of tries. For example, a bank uses it to detect if somebody is doing frauds, recommendation systems. So clicks are there really interesting as well as subgraphs.
Yeah.
And they use it regularly in this context in papers.
That's true. Yeah. More reading material.
okay, any more questions?
I haven't thought to apply these comparison schemes to strings or that to variable int data.
No, it's just for now. Well, running encoding of course works for anything. That doesn't really matter. But
I can use more branches, but I'm not sure. Okay. More readings to go.
I have a final one. Is there any work on doing this with non-equality joints? Non-equality joint predicate?
wouldn't be able to give you an answer to that, to be honest. It's always about equality joints if you look at it, but
It's evil, but what I'm thinking of is that, like with inequality joints, you always have that. You know, if you just have a two-way inequality joint, it's very likely that you have a huge result. However, as soon as you get these kind of particularly cyclic patterns, there's a good chance that that initial idea that intermediate results of two-way joints are larger than the final result might be even more pronounced. That you get situations where you have like insanely blowing up intermediate results, just as you have in like a multi-dimensional trace, multi-dimensional range trace, where the final result is much smaller than any single of those.
Yeah.
And here you also have like the conjunction of the various joint predicates might actually give you a rather concise, close to kind of global equality joint-like result, whereas all intermediate results are even bigger than that. And that might actually be interesting in looking into, if it hasn't been done yet, whether these occur in practice in the first place, and, but if so, whether these techniques are maybe even more applicable and useful than in equality cases.
Yeah. Yeah, good point.
And then they could actually be not only on paper optimal, but in practice. That would be good. But there is quite some work on multi-way joints anyway, so they need to be considered as well.
Yeah, I'll get to that.
Okay, I think we can finish the presentation now.
Yep.
Thank you, Richard.